Hi, this is John Isles and welcome to Geometer's Paradise. Today we're going to be looking at Unit 6, Lesson 4C. So this is the third in a series about side, 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 and side angle side, triangle congruence. Today you're going to look at when do you pick side, 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 and when do you pick side angle side. Whoops, and I just jumped two slides at once. Okay, so when should side angle side be tried over side, side, side? All right, now if you think about this question just a little bit, it makes the answer makes perfect sense, okay? You choose side angle side when there's an angle. Oh, of course. I feel like every video I make, I'm commenting on how this tablet is great when the pen works. So when there is an angle. No angle? Don't use side angle side. If there is an angle, use side angle side. Okay, so here we have a given on the left. We have K as the midpoint of HW. HAW is isosceles with base HW, and we want to show that HAK is congruent to WAK. On the right, we have AK perpendicular to HW, AK bisects HW, and show that HAK is congruent to WAK. First of all, we have a reflexive side right here. Sorry. We have a reflexive side, so that's 1S. Okay? Midpoints give us an S. Isosceles triangles give us an S. We're going to learn in a few days that they'll also give us an A, but right now they just give us S's. Perpendicular lines give us an A. Bisecting a segment gives us an A. Wow, that was bad. Bisecting a segment gives us an S, not an A. So this one over here is side, side, side. This is a side, side, side set. This one over here is an SAS. It has the potential to be an SAS set. You have to be careful and make sure that the angle fits between the two sides and that it's not outside of it. Remember, angle side, side is not a thing. Okay? Side angle side is. So make sure the angle is squished between the sides. All right. So here's our setup. We have a reflexive side right here, XY. Okay. LX being parallel to YN. That produces an angle. Parallel lines produce congruent angles. And then, of course, this is a set of congruent sides. So I have the potential for this to be a side angle side proof. All right, the first side is XY congruent to itself by the reflexive property. The second is LX congruent to YN. Okay, because it's given. So that's this side congruent to this side, and of course XY is congruent to itself. So the angle that is smashed between them are these two angles. And since LY I totally marked that wrong, didn't I? Yeah, hang on. This is only slightly embarrassing. LX is this side. YN is this side, which means the angles smashed between them are here and here. And since LX is parallel to YN, that means the angles formed by the transversals are congruent. So these are alternate interior angles. So we can say that angle LXY is congruent to angle NYX. This is the alternate interior angles theorem brought to you by LX parallel to YN. Okay, so that's kind of cool. One way to view this, if you just look, I'm going to make heavy lines here. All right. Okay, so you should see now that the angles have the small s connecting them, so that makes it an AIAT connection. All right, let me darken this a little bit more. All right, so you see where the transversal comes through and your alternate interior angles. All right, there you go. Now let's get rid of that. There, whoops, too many undos. All right, so this means that triangle LYX is congruent to triangle NXY. Wow, sorry, try that again. NXY by side, angle, side, triangle congruence. Okay, next up. Whoa, this is craziness, right? Okay, just relax, let's have a look. All right, so my first given is that ZEB is isosceles. That's a side. And then my second given is that AIR is isosceles. That's a side. And then my third given is that ZA is congruent to RB. That's a side. So this looks like it could very possibly be a side proof. Let's go in and mark off what we're congruent. So ZA is congruent to RB. That was our given. ZEB, which is the large isosceles triangle, is isosceles with base ZB, which means that Z is congruent to EB. And AIR is isosceles. AIR is this triangle right here. Okay, so that this side is congruent to this side. We want to prove that triangle ZEA is congruent to triangle BER. There is a harder version of this picture, but ZEA is this triangle right here, and EA and BER is this triangle right here. So, from ZEB, ZE is congruent to EB, isosceles triangle. From AIR, AE is congruent to ER, isosceles triangle. ZA is congruent to RB, given. And that means that ZEA, the triangle ZEA, is congruent to the triangle BER by side congruence. Okay. HAW is isosceles with base HW. This is a side. AK bisects segment HW. This is a side. And we have the reflexive side right here. So it looks like we've got another side proof. AK is the cutter. AK is the sword that is cutting HW into two pieces. So HK is congruent to KW, AK to itself, and the isosceles triangle HA is congruent to AW. So AK is congruent to AK, reflexive. HK is congruent to KW, bisector, and HA is congruent to AW, isosceles triangle. That means that triangle hack, HAK, is congruent to triangle WAC, WAK. All right. Okay, here we go again. Now this one's very interesting proof because we actually have enough to do our new type of theorem as well. But this is intended to give us an angle. This is intended to give us a side, and this is intended to give us a side. Okay, so this looks like it's going to be a side angle side proof as well, and it well could have been because of the vertical angles. But check it out. A is the midpoint of VN, means that you're going to have VA congruent to AN. That's one of your sides. The other one is that RN is congruent to VE. So if you were to take the two vertical angles like we normally do, you would have an angle side theorem. Okay? That's not going to work. Here we go. We've got these two angles need to be congruent, and we can get them congruent because these two sides are parallel, and we have that Z shape that we need. Okay, we have the Z shape that we need with the parallel lines in order to get the alternate interior angles. So we say RN is congruent to VE given. We have angle RNA congruent to angle EVA. This is an alternate interior angles theorem because RN is parallel to VE. And then we have NA is congruent to AV by midpoint theorem, which means that triangle RAN is congruent to triangle EAV. Okay, so another side angle side proof. Let's see, do we have anything else? Oh, we do. It just keeps going. How many more? That's it. One more. Okay, very good. Is it bad that I made this slideshow and don't know how long it is? I mean, it was 2 years ago, though. Seriously. Perpendicular lines, angles. Bisecting a segment, sides. Reflexive side. So, side, angle, side. AK to AK. Mental note for next year, rename all of these triangles so that they're not all the same every time. All right, and HK, AK is bisecting, AK is coming through and cutting HW, so HK and KW are both congruent. HK is congruent to KW, bisector. Now, perpendicular lines form congruent adjacent angles. So angle HKA is congruent to angle WKA, all right, because perpendicular. All right, so then triangle HAK is congruent to triangle WAK by the side angle side theorem. All right, there it is. I will see you guys tomorrow in class.